All right, so hope everyone had a good lunch. Welcome back to the talks. So today I'm going to be talking about, as Daryl mentioned, taking Eclipse OMR JitBuilder to a language near you. Otherwise said, I'm going to be talking about recent work that has gone on to create language bindings for JitBuilder so that it's callable from a variety of programming languages. I will be first doing an introduction to just what I'm going to be talking about, doing a recap of what JitBuilder is, how it's evolved, some of the projects we've worked on, some of the challenges and modifications we made to it, how we came up with the idea of creating language bindings, some of the work that went into deciding how these would work. And then I will be talking about some implementation and methodologies of these language bindings, and I will be concluding with just a quick status update of the work. So getting right into it, first just a slide about me. For those that don't know me, I'm a software engineering graduate from the University of Calgary. As Daryl mentioned, I work for IBM Runtimes. Most of my work has focused with the Eclipse OMR compiler. The Eclipse OMR compiler technology, and JitBuilder specifically. I created Lua Vermela, which is a JIT compiler for Lua that I actually presented at this conference 2 years ago. And I also worked on WebAssembly, which was presented this morning twice. So jumping into the meat of this presentation, JitBuilder, at the highest possible level, it's a component of Eclipse OMR. It's a framework for building JIT compilers, and that's how we've traditionally thought about it. It allows us to leverage the Eclipse OMR compiler technology. It provides a high-level interface for generating the Eclipse OMR compiler's intermediate language, or IL, and provides same defaults for things like optimization, code generation, and other tasks that we expect a JIT compiler to do that are not necessarily specific to a particular language, thereby alleviating some of the pain points of having to create a JIT compiler. It's written in C++, following the trend of the underlying compiler technology. And lastly, being a component of Eclipse OMR, one of the very important goals of JitBuilder is it tries to take the compiler technology to language runtime developers, as opposed to requiring developers to bring their technology to us. So the goal is to make adoption easier not only for new languages being created, but also for existing programming languages and language runtimes. And part of this involves not requiring that all of the existing code be retrofitted on top of the OMR ecosystem when not required. So there have been several proofs of concept of JitBuilder JIT compilers integrations, including CSOM or SOM++, which was mostly been worked on by Charlie Gracie from the Ottawa team, Lua, that I created myself 2 years ago, as I said. We've created prototypes for Swift, Ruby, the Rosie pattern language, and WebAssembly, which again we heard about this morning. Through these projects, we've learned a lot of lessons about what works in JitBuilder and what hasn't worked so well, which has led to naturally for JitBuilder to evolve and continuously improve. One of the major aspects that has been improved is the IL generation services. Over time, as we found more problems to solve, we've identified specific services for generating certain kinds of IL that have ultimately increased the descriptive power of the JitBuilder API. We've also improved the IL generation process so that it is actually now easier and faster to optimize the generated IL, resulting in faster, higher quality code once the JIT compiler is done running. There have been lots of other improvements done. I don't have enough room on one slide to list them all, so I'm going to move on to the main topic of this presentation, which is language bindings. So diving right in, why did we want to create language bindings for JitBuilder? The first obvious answer is, with that goal of taking the compiler technology to developers, we want to allow them to write JIT compilers in languages other than C++, since there's many language runtimes that are not written in C++. So being able to write a JIT compiler in C, Swift, Rust, or conceivably any other language can make the technology more appealing to these language runtime developers. At a very meta level, we can start thinking about writing, say, a Java JIT compiler in Java, or a Ruby JIT compiler in Ruby, or even a Lua JIT compiler in Lua. For anyone interested in recursion, thinking about the implications of this can provide hours of entertainment. If recursion is not your thing, maybe we can start thinking about only implementing parts of the JIT compiler in the target language, such as helpers for controlling the compiler. For example, we might choose to implement functions for enabling and disabling the JIT in the target language, or even the function for requesting that a particular function be compiled. And finally, taking this a step further, we can move away from thinking of JitBuilder as a framework for writing JIT compilers and more as a general purpose workload acceleration framework. So for performance sensitive tasks, we can start generating native machine code from the target language without having to resorting to writing C extensions or modules for the target language. For anyone interested in this, Mark Studley is going to be talking about this a week from now at Splash, I believe. So yes, apparently I have 12 minutes left of battery, so I do have my charger in my backpack, but if you could grab that for me. So moving on, some of the design goals for these language APIs have been first to maintain backwards compatibility with the existing C++ API. We don't want to require that all of these projects that have already been built on top of JitBuilder have to change all of their code just because we decided to allow other languages to use the technology. Another goal has been to expose as much of the JitBuilder API as possible to other languages so that language developers are not penalized if they choose to use a language other than C++. We also want to minimize the cost of having to update n different bindings. Since JitBuilder is a technology that changes fairly regularly, we don't want to have to work too hard to make JitBuilder API changes work across n different language bindings. And an extension to this goal is the idea that we want to provide a separation between the client API and the JitBuilder underlying implementation. Now here I will, for the rest of the presentation, when I say client API, I specifically mean the language binding for the public API. Otherwise said, the API that is provided by a particular language binding. Hopefully that's clear. And finally, the last requirement we want is for these language bindings to be fairly easy to debug. JIT compilers are complicated programs. JitBuilder simplifies creating JIT compilers, but there's nevertheless some amount of debugging that usually has to happen. So now, a brief pause and make sure everyone is with me on this. Okay, good. So with these design goals in mind, we considered a few alternatives. The first one being to write language bindings manually. The one advantage here would be that we would have complete control over how the language bindings work. And while that would be nice, there are significant disadvantages in the likelihood of introducing bugs when writing the large quantity of code required for language bindings. And ultimately, this would result in very high maintenance costs every time we change the JitBuilder API. So the next alternative we considered was to use an existing tool that generates language bindings, such as Swig. And we actually tried a few options, but we found that the tools either struggled with certain aspects of the JitBuilder API or did not support them at all. For example, callbacks were particularly challenging. And then, in addition, we found that with most tools, the generated code was generally difficult to understand and debug, which doesn't really follow what we are trying to achieve, and it breaks one of our design goals. So finally, what we decided to do was to write a custom language binding generator. Our rationale being that it would provide us the benefit of not having to maintain n different language bindings manually. We would need to maintain the generators, but really the only work we would have to do would be to update the generators when we change the JitBuilder API in such a fundamental way that the generator does not currently handle. And hopefully the assumption is this doesn't happen all that often. And to support that point, the JitBuilder API is fairly consistent across its surface. So it has a lot of services that work in very similar ways, which in turn suggests that maybe there's an opportunity for automating binding to these services. We can also specialize the tool to handle JitBuilder specifically. So we can teach it to handle callbacks specifically and ensure that these concepts get mapped to, I guess, patterns or idioms that are more natural in the target language. We also get full control over the generated code, so we can make decisions about what trade-offs we want between debuggability and performance, for example. And finally, the big disadvantage of this approach is that, of course, there is a very high initial cost of implementing the generators for a particular language. This said, we actually went ahead and did it, mostly. So the first thing we thought about was what doesn't work with the existing tools and what can we do differently? So a typical tool like Swig will read C and C++ code and then generate language bindings for it. And users then call or link against the generated bindings. The problem is the tools will struggle to handle complex or unconventional looking code. Since these tools are very general purpose, they tend to target the most common denominator, and deviating from that can lead to poor results, as was with our case. And part of the fundamental problem is that source code, especially in C and C++, does not always communicate the conceptual aspects of what the code is trying to do. So the approach we chose instead is to have a separate description of the JitBuilder API written in JSON, then have the generator read the API description and produce bindings from that. And then the produced bindings or client APIs act as the interface between users of JitBuilder and the underlying JitBuilder implementation. Any questions so far? No, everyone's still good, still following along? Okay, now we get to the more complicated part. So we created a high-level plan for how we were going to approach creating this tool. And the first step was to define a schema for the API description format. The idea being that then we can validate this schema against the JSON schema project, For those that are not familiar with JSON schema, taking the first sentence from their front page, JSON schema is a vocabulary that allows you to annotate and validate JSON documents. So once we have a schema, we can actually start describing the JitBuilder API in JSON following the schema. And importantly, we can validate the description against the schema. This allows us to catch right away a API description that is ill-formed or that doesn't follow the structure we expect, which avoids us having to debug the very peculiar things that can happen if you feed invalid JSON into, say, a Python script that expects things to look a certain way. The next step after that was to write a C++ client API generator. And we chose to write this first generator in Python for ease of use and availability across platforms. And the generator itself was validated by writing unit tests, which Python provides a built-in module for. And the generated code was also tested against the existing JitBuilder test suite. This was important for us because it's a way of ensuring we maintain our goal of backwards compatibility with the C++ API. So we can fairly confidently assume that if the tests continue to pass, then it's very likely that other users of JitBuilder will be able to simply start consuming the generated C++ API and experience a minimal number of issues, if any. Once we have a C++ API, we can start working on a C API, since it's likely going to work very similar to C++, and by that I mean it's less different than picking another language. So C was kind of our next logical goal, and for testing purposes, we want to reproduce the JitBuilder test suite in C. We'll see how much work that actually is in the future. And once we have a C client API, we can start working on client APIs for other languages. The rationale being that binding to C is usually easier than binding to C++, which is a much bigger, more complex language. So this brings up an interesting problem, which is that JitBuilder relies heavily on C++ inheritance. This is one of the aspects of the JitBuilder API that existing tools struggle with. So how can we map these JitBuilder inheritance hierarchies to C while maintaining compatibility with the existing API so that users of C++ can continue to work the way things worked before? We came up with a solution. It is probably the most complicated part of this presentation, so I'm going to try and make sure that people keep up with me and not lose anybody. At a very high level, what we did was modify the JitBuilder implementation to allow overriding to happen in C using function pointers and callbacks. So instead of overriding a virtual function, we set a new callback that then gets called via a function pointer. I will explain this in more detail in the following slides. And once we have this mechanism in place, we can think about reproducing the C++ API, but using the C overriding mechanism under the hood. This will require us to have a one-to-one mapping between objects on the C++ client API and the JitBuilder implementation. Everyone with me so far? Kind of? Okay, hopefully the next few slides are going to clear this out. Let's go through an actual very high-level example of how this is going to work. So here on the left, we have the client API, which has a class called base and a virtual function called foo. That's just what the public API has. We also have a callback that corresponds to foo. and I will explain how this callback is used in a minute. On the right side, we have the implementation, which, following this idea of creating a one-to-one mapping of objects, also has a class called base with a virtual function foo. And notice that there's actually two functions called foo. There's the virtual function capital F foo and a non-virtual function lowercase f foo. We need these, and these two are going to fill different purposes. So capital F foo will contain the actual body of the implementation of foo, while lowercase f foo will only contain the code required to handle the callback and C side extensions. So the distinction between capital F and lowercase f is just a convention we came up with. Maybe not the least confusing solution, but it's what we have. So it's what I will use in this example. Now, the important rule to remember is on the implementation side, anywhere where we would like to call capital F foo, we must instead call lowercase f foo. And here's why. Lowercase f foo, when called, will invoke the callback that is set by the client API when constructed or initialized. That's kind of an implementation detail when that happens. We then expect the callback to invoke the client-side function of foo, and then the client side is going to forward the call back to the implementation side. Okay, everyone with me so far? Does this make sense? Okay, good. All right. So hopefully later on it will make sense why we need to do this roundabout calling. Let's look at a more, actually before I move on, looking at things from the client side. So if you think about just how a user is going to experience this, if they want to call foo, they just call capital F foo because that's the only thing that they have on the client side, and the call gets forwarded to the implementation. So as far as users are concerned, nothing has changed other than possibly things being in a different namespace, but that's something that is hopefully fairly easy to handle. So let's look at a more complicated example now where we have a base class and a derived class. So again, we have our base class on both the API client and implementation side. And we also have a derived class on the client API and implementation side, both of which override the virtual function foo. And we also create a different callback now that will correspond specifically to our derived class. Notice that on the implementation side, we don't override lowercase foo. This is important because we don't actually need to override it, since what we will do instead is just set the new callback we've created. So that now, on the implementation side, when we call lowercase f foo, it will invoke the new callback we've created, which will invoke the client-side override of foo, which will then forward the call back to the implementation side of foo. Everyone still with me? Okay, good. Looking at things again from the client side or from the user's perspective, nothing still changes still. If we want to call the derived override of foo, we can still just call that, and the call gets forwarded for us to the implementation side. Now we look at kind of the magic point that almost justifies why this complexity is warranted, which is what happens if the user chooses to override capital F foo. Notice that because this is a user override, the class only shows up on the client side or the user's side, not on the implementation side, because this is a user extension. So the user overrides foo with their own implementation. And on the implementation side, when we call lowercase f foo, it will invoke the same callback we saw before. The callback will invoke the derived override of foo as before. And then importantly, virtual function dispatch from C++ will forward the call down to the user's override for free. So again, as far as the user is concerned, they can continue to just use the public API as they did before, nothing changes, and we can still maintain this overriding mechanism using callbacks. Now, I'm sure I know what you're thinking at this point. Do we really need all of this complexity just to call a function? Well, yes and no. So to explain what I mean, I'm going to bring back two of the very important design goals I had several slides ago. The first one being maintain backwards compatibility for the C++ API. Hopefully it's clear from my examples, although I didn't show every possible use case, that we do, as far as the user is concerned, things will continue to work the way they did before. So this goal we've achieved. And it turns out that in terms of the changes we had to make to JitBuilder to make this work, they were mostly unintrusive. So we really only had to add in a few functions and then rename a bunch of other things, which are things that we can actually use just existing tools to do. There's quite a few automated refactoring tools that will do this kind of work for us. And finally, the second design goal, which was to provide a clear separation between the client API and implementation, was also achieved. In fact, in my diagrams, I have a dashed line separating the two. So we have really separated these two quite well. And the reason this is important is because we can now start thinking about how we can change the implementation side and also not affect the public API. So hopefully, now that this has been set up, we can simplify the underlying implementation and still maintain the current publicly visible API. Everything clear so far? Excellent. So now, quick status update about what the current state of the work is. The C++ generator is essentially complete. It was contributed to the Eclipse OMR repository in 2 pull requests. The first one actually added the generator itself, so the Python program that generates the C++ client API, as well as the JSON schemas and JSON API description for JitBuilder. And this pull request has already been merged. The second pull request updates the JitBuilder implementation to follow that calling contraption I went through in the few examples. And this PR, we're still working through a few kinks, so it's still open and will hopefully be merged relatively soon. There is ongoing work to create a C binding generator using a similar approach we used for the C++ generator. And an extension of this work is to try to create Python bindings, or rather a Python binding generator based on the C binding generator. So some future work. First of all, we would like to clean up some of the implementation side code. As you've hopefully guessed, it is rather complicated and convoluted, and sometimes it's a little difficult to keep track of where in the loop of a function invocation you are. So cleaning this up will help make things better in the future. But of course, we also want to start working on creating more bindings. So bindings for Java, Rust, Lua, those are some of the languages on my personal list. And hopefully, in the not too distant future, you will be able to start taking advantage of the JitBuilder API in whatever your favorite language might be. Okay, so with that, thank you for listening to my rambling. And do you have any questions? Really, it was that clear? Okay.
Yeah. Okay. Thank you, Leo.
All right.